When adding a 4-way high-voltage switch to provide power to 3 transformers that feed 3 buildings, there are 2 primary options to consider. Firstly, connecting the high-voltage lines to the switch side of the switch, and secondly, connecting them to the unswitched side. Each option presents distinct advantages and disadvantages, which must be evaluated in light of the specific needs of the installation, safety considerations, reliability requirements, maintenance protocols, and cost implications. Option 1 involves connecting the high-voltage lines to the switch side of the 4-way switch. The primary advantage of this configuration is that it provides greater isolation and flexibility in controlling power to each transformer. In the event of a transformer failure or the need for maintenance, the power supply to that specific transformer can be isolated without disrupting the operation of the other transformers. This isolation capability enhances safety by allowing personnel to work on one transformer while the others remain energized, minimizing the risk of electrical hazards. Furthermore, this approach facilitates easier maintenance, as individual transformers can be taken offline for inspection, repair, or replacement without affecting the overall power distribution system. From a safety perspective, connecting the high-voltage lines to the switch side of the switch offers a higher degree of protection. The ability to completely isolate each transformer from the power source significantly reduces the risk of accidental energization during maintenance or repair activities. This isolation also helps to prevent the propagation of faults from one transformer to another, limiting the potential for cascading failures and minimizing the overall impact on the electrical system. In terms of reliability, connecting the high-voltage lines to the switch side of the switch allows for selective isolation of faulty equipment. If one transformer experiences a failure, it can be quickly isolated from the system, preventing the fault from spreading to other transformers or connected loads. This isolation capability helps to maintain the overall integrity of the power distribution system and ensures that the other transformers continue to operate without interruption. Maintenance is simplified with this configuration, as individual transformers can be taken offline for inspection, testing, or repair without affecting the power supply to the other transformers. This allows maintenance personnel to perform their tasks safely and efficiently, minimizing downtime and reducing the overall cost of maintenance. However, Option 1 may involve more complex wiring and a higher initial cost compared to Option 2. The additional components required for switching and isolation can add to the overall expense of the installation. Option 2 involves connecting the high-voltage lines to the unswitched side of the 4-way switch. This configuration is characterized by simpler wiring and a lower initial cost. The absence of switching devices on each high-voltage line reduces the number of components required, simplifying the installation process and lowering the overall cost. A key advantage of this approach is that it provides a redundant power supply to all transformers. In the event of a switch failure, the transformers will continue to receive power from the unswitched side, ensuring continuous operation. This redundancy enhances the reliability of the power distribution system, particularly in critical applications where uninterrupted power supply is essential. From a reliability standpoint, connecting the high-voltage lines to the unswitched side of the switch provides a higher level of assurance. The redundant power supply ensures that the transformers continue to operate even if the switch fails. This is particularly important in applications where downtime is unacceptable, such as hospitals, data centers, and other critical facilities. The disadvantage of this configuration is that it does not provide the same level of isolation and flexibility as Option 1. In the event of a transformer failure or the need for maintenance, the entire system may need to be de-energized to ensure safety. This can lead to prolonged downtime and disruption of power supply to the connected loads. The absence of individual isolation also increases the risk of fault propagation, as a fault in one transformer can potentially affect the other transformers and connected loads. Maintenance can be more challenging with this configuration, as the entire system may need to be de-energized to perform maintenance on any of the transformers. This can result in significant downtime and disruption of power supply, especially in applications where continuous operation is essential. Furthermore, the lack of individual isolation can increase the risk of electrical hazards during maintenance activities. Safety is a critical consideration when choosing between these two options. Option 1, with its greater isolation capability, generally provides a higher level of safety. The ability to isolate each transformer individually reduces the risk of accidental energization during maintenance or repair activities. This isolation also helps to prevent the propagation of faults from one transformer to another, limiting the potential for cascading failures and minimizing the overall impact on the electrical system. Reliability is another key factor to consider. Option 2, with its redundant power supply, offers a higher level of reliability in terms of continuous operation. The transformers will continue to receive power even if the switch fails. However, Option 1 provides better reliability in terms of fault isolation, preventing the spread of faults and maintaining the integrity of the power distribution system. Maintenance requirements should also be taken into account. Option 1 simplifies maintenance by allowing individual transformers to be taken offline for inspection, testing, or repair without affecting the power supply to the other transformers. This reduces downtime and minimizes the overall cost of maintenance. Cost is a significant factor in most installations. Option 2 is typically less expensive to implement due to its simpler wiring and reduced component count. However, the long-term cost associated with maintenance and potential downtime should also be considered. NEC 710.12 provides guidelines for the installation of high-voltage equipment. This section of the code addresses various aspects of high-voltage installations, including grounding, overcurrent protection, and equipment ratings. When choosing between Option 1 and Option 2, it is important to ensure that the installation complies with all applicable requirements of NEC 710.12. The specific requirements of the local utility, JCPL in New Jersey, must also be considered. JCPL may have specific regulations or guidelines for high-voltage switching arrangements that must be followed. It is essential to consult with JCPL to obtain the necessary approvals and ensure that the installation meets their requirements. Based on the advantages and disadvantages discussed above, Option 1, connecting the high-voltage lines to the switched side of the switch, is generally recommended for providing power to multiple transformers. This option provides greater flexibility, isolation, and safety. The ability to isolate individual transformers for maintenance or in the event of a failure is a significant advantage, particularly in critical applications where uninterrupted power supply is essential. However, the specific requirements of the installation and the local utility must be carefully considered before making a final decision. It is important to consult with qualified electrical engineers and JCPL representatives to ensure that the installation meets all applicable codes, standards, and regulations. In summary, adding a 4-way high-voltage switch to provide power to 3 transformers requires a careful evaluation of the available options. Connecting the high-voltage lines to the switched side of the switch provides greater isolation, flexibility, and safety, while connecting them to the unswitched side offers simpler wiring, lower cost, and redundant power supply. The choice between these options depends on the specific requirements of the installation, safety considerations, reliability requirements, maintenance protocols, and cost implications. Compliance with NEC 710.12 and local utility regulations is essential. Option 1's enhanced safety, stemming from its superior isolation capabilities, is a critical consideration, especially when working with high-voltage systems. By isolating individual transformers, the risk of accidental energization during maintenance or repair is significantly reduced. This isolation also acts as a barrier against the propagation of faults, preventing cascading failures that could compromise the entire electrical system. In terms of reliability, Option 2's redundant power supply offers a distinct advantage. The continuous power flow to the transformers, even in the event of a switch failure, ensures uninterrupted operation, a crucial factor in environments where downtime is unacceptable. However, Option 1 provides a different kind of reliability, one focused on fault containment. Its ability to isolate faulty equipment minimizes disruptions and maintains the integrity of the power distribution system. Maintenance procedures are streamlined with Option 1. The ability to isolate individual transformers allows for safe and efficient inspection, testing, and repair without affecting the power supply to other components. This reduces downtime and minimizes maintenance costs, contributing to the long-term efficiency of the system. While option 2 might seem more cost-effective initially due to its simpler wiring and fewer components, a comprehensive cost analysis should also consider the potential expenses associated with downtime and system-wide maintenance. NEC 710.12 serves as a guide for safe and compliant high-voltage installations. Consulting with JCPL in New Jersey is paramount to ensure adherence to local regulations and to secure the necessary approvals for the proposed installation. By carefully weighing the advantages and disadvantages of each option and adhering to relevant codes and regulations, a safe, reliable, and efficient high-voltage switching solution can be implemented to meet the specific needs of the campus. The focus on safety when selecting option 1 is important because high-voltage systems pose significant risks. The ability to completely de-energize a transformer before performing any work on it is invaluable. This reduces the potential for arc flash incidents, electrical shocks, and other hazards. The isolation also prevents backfeeding, where energy from another source flows back into the transformer, potentially endangering workers. The reliability benefits of option 2 are most apparent in situations where even brief power interruptions can have serious consequences. Hospitals, data centers, and manufacturing plants often rely on uninterrupted power to maintain critical operations. The redundant power supply ensures that these facilities can continue to function even if the primary switch fails. However, it is important to note that option 2 does not eliminate the need for maintenance. Switches and other components still need to be inspected and maintained regularly to prevent failures. The simplified maintenance procedures associated with option 1 can significantly reduce the overall cost of ownership. By allowing individual transformers to be isolated, maintenance personnel can perform their tasks more quickly and efficiently, minimizing downtime and reducing labor costs. Furthermore, the ability to isolate faulty equipment can prevent minor problems from escalating into major failures, further reducing maintenance expenses. The initial cost savings associated with option 2 should be weighed against the potential long-term costs associated with downtime and system-wide maintenance. A thorough cost-benefit analysis should consider all relevant factors, including labor costs, equipment costs, downtime costs, and potential safety risks. NEC 710.12 provides detailed requirements for the installation of high-voltage equipment. These requirements cover a wide range of topics, including grounding, overcurrent protection, and equipment ratings. Compliance with NEC 710.12 is essential to ensure the safety and reliability of the electrical system. Consulting with JCPL in New Jersey is crucial to ensure compliance with local regulations. JCPL may have specific requirements for high-voltage installations that are not covered by NEC 710.12. It is important to obtain the necessary permits and approvals before beginning any work on the electrical system. The decision of whether to connect the high-voltage lines to the switched or unswitched side of the switch is a complex one that requires careful consideration of all relevant factors. By weighing the advantages and disadvantages of each option and consulting with qualified professionals, a safe, reliable, and efficient high-voltage switching solution can be implemented to meet the specific needs of the campus. Remember that a crucial element of option 1 is the enhanced safety features. The ability to isolate individual transformers not only protects maintenance personnel, but also reduces the risk of damage to equipment and property. Fault isolation prevents the spread of electrical disturbances, minimizing the potential for fires, explosions, and other catastrophic events. While option 2 offers a redundant power supply, this redundancy comes at the expense of flexibility and control. In the event of a transformer failure, the entire system may need to be shut down to perform repairs. This can result in prolonged downtime and significant disruption of operations. Simplified maintenance procedures associated with option 1 not only reduce costs but also improve the overall safety of the electrical system. By allowing individual transformers to be isolated, maintenance personnel can work on de-energized equipment, minimizing the risk of electrical shock and other hazards. A comprehensive cost analysis should consider the long-term benefits of option 1, including reduced maintenance costs, improved safety, and minimized downtime. While the initial cost of option 2 may be lower, the long-term costs associated with downtime and potential safety risks can quickly outweigh these initial savings. NEC 710.12 provides guidance on the selection and installation of high-voltage equipment, but it is not a substitute for sound engineering judgment. Qualified electrical engineers should be consulted to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. Consulting with JCPL in New Jersey is essential to ensure that the electrical system meets the specific requirements of the local utility. JCPL may have specific regulations regarding the type of equipment that can be used, the location of transformers, and the grounding requirements. The addition of a 4-way high-voltage switch to provide power to 3 transformers is a complex project that requires careful planning and execution. By considering all relevant factors, consulting with qualified professionals, and adhering to all applicable codes and standards, a safe, reliable, and efficient electrical system can be implemented to meet the needs of the campus. Furthermore, in evaluating the options, consider the long-term scalability and adaptability of the system. Option 1, with its greater flexibility, might be more suitable if there are plans to add more transformers or modify the electrical system in the future. The ability to isolate individual transformers makes it easier to integrate new equipment and perform upgrades without disrupting the entire system. In contrast, option 2, with its simpler design, might be more difficult to modify or expand. The absence of individual isolation can make it challenging to integrate new transformers or modify the existing wiring without shutting down the entire system. Also, consider the impact of voltage fluctuations and power quality on the connected loads. Option 1, with its ability to isolate individual transformers, can provide better voltage regulation and power quality. If one transformer experiences a voltage sag or other power quality problem, it can be isolated from the system, preventing the problem from affecting the other transformers and connected loads. Option 2, with its redundant power supply, may not provide the same level of voltage regulation and power quality. If the switch fails, the transformers will continue to receive power from the unswitched side, but the voltage may be lower or the power quality may be degraded. Evaluate the environmental conditions in which the electrical system will be operating. If the system will be exposed to harsh weather conditions such as extreme temperatures, humidity, or corrosive substances, it is important to select equipment that is designed to withstand these conditions. Option 1, with its greater complexity, may be more susceptible to environmental damage than option 2. The additional components required for switching and isolation can provide more points of failure. Option 2, with a simpler design, may be more robust and less susceptible to environmental damage. Work with qualified electrical contractors who have experience installing high-voltage equipment. High-voltage installations require specialized knowledge and skills. It is important to select contractors who are licensed, insured, and have a proven track record of success. Qualified contractors will be able to properly install the equipment, ensure that it is grounded correctly, and verify that it meets all applicable codes and standards. Lastly, develop a comprehensive maintenance plan for the electrical system. High-voltage equipment requires regular inspection and maintenance to ensure that it is operating safely and reliably. The maintenance plan should include regular inspections, testing, and cleaning of the equipment. It should also include procedures for responding to emergencies such as power outages or equipment failures. A well-designed and maintained electrical system is essential for providing safe, reliable, and efficient power to the campus. By considering all relevant factors and consulting with qualified professionals, an electrical system can be implemented that meets the needs of the campus for years to come.